By one man. It's my pleasure today to introduce Dr. Steve Trimberger, who, a brief bio, begins by saying he got his PhD from Caltech in 1982. There he went to work for VLSI Technologies, and then, like many of us, realized VLSI technology was a dead end, and went to Xilinx in 1988, and has been there ever since as many things. He's well known for being one of the key architects on the Xilinx 4000. You invented LutRam, did you not?
I was on that group.
You're in the group. An important invention. And was the key architect on the follow-on to that 4000 EX.
Okay.
And has been a participant in the architectures ever since then, coming out of Xilinx, and is known to many of us in the academic community as he's been a key interface into all the different conferences, offering insights from his technical perspective, which is broad and deep across circuits, architecture, and software. He holds 210 patents and counting. They ratchet up every few days. And have I missed anything?
There's some SETI stuff I do.
Oh, and he's interested in SETI, and we'll hear about that today. Please welcome Steve Trimberger.
Well, thank you. I'm like Jonathan said, I have actually 3 talks, and if we get to them all, and there's still people here, I could keep talking. The first one is this one I call 3 Ages of FPGAs, and it's a bit of a history. And I know there are people here who have some history in the FPGA business. I've been in 26 years. Something I've noticed about histories, particularly histories that I have personal knowledge about, when I read about them in books, that's not what happened. So I always disagree with other historians. So I will expect that those who have also lived this history will disagree somewhat with what I say. And so that I use Kurt Vonnegut's response, which is let him write his own book. But what we'll talk about is here. I'm going to talk about what I experienced, and I'm not going to talk about history, just what happened, because that's boring. I'm going to talk about why it happened, and because I think that's interesting. And so that's something that you could potentially carry on and years forward say, okay, something's different happening. So the first thing I'm going to talk about is, well, if we get to the end and I haven't answered all your questions, or you can't think of a question, you could use one of these. These are questions that might get answered through this history. They may become apparent. I may explicitly say them, or maybe I won't. But anyway, we'll talk about various aspects of FPGA's histories and things that have happened. Now, I could talk about FPGA history, and I could put up this graph. I'm very proud of this graph, and everybody in the FPGA business is very proud of this graph like this. Oh, look at this. Over the last 30 years, actually it's more than 10,000, it's almost 100,000x now, more logic. They got a lot cheaper. Power's dropped dramatically. Performance, spectacular. This is great stuff. And you'll sit there and say, yes, Steve, you didn't do any of this stuff. This is Moore's Law. I can see that just reading it off the graph. And you'd be almost right. It is about process technology scaling. That's a big lever. And that was one of the biggest observations at the birth of FPGAs, that you could take advantage of that, and FPGAs could take advantage of that. But really what happened was, while we had process scaling this whole time, the effects on what we build, the effects on the applications we run, the effects on the software we have been different. And so I'm going to talk about that. We had quantitative changes that led to qualitative changes in all those attributes. So I divided it up into 3 distinct phases, ages. I call them ages: the age of invention, the age of expansion, and the age of accumulation. And you will notice that it doesn't lead up to the present day. And there are a couple of good reasons for that. One good reason for that is that it's really hard when you're in the middle of one of these events to realize that you're in the middle of something specific. It just feels like a law of nature. It's going to go on forever, and you proceed, and you will see that as we go through this. And it's only looking backward that you really kind of understand that, well, what really happened, and what was really going on then, and what was special about it. So that's one first thing. The second thing is, I will talk about 2008 and beyond when I get to the end. So you might want to hang on and pay attention to the end. The first thing, I get a lot of questions about, what's the big deal about FPGAs? There was programmable logic before there were FPGAs. Programmable logic, kind of looked sort of like this. I had an array of these little dots. This is a wired AND structure. Well, it's a wired NOR structure, and it's an OR, but that's AND OR, and you can build any function you want. Beautiful, worked great. There are several nice aspects of this. If you were a semiconductor manufacturer, and there were a lot of them then, back in the 80s, and you could build memories, this looked a lot like a memory, so you could build these. You can go into the programmable logic business pretty quickly. They generally didn't have any software development, and so there were a couple of companies that did software for that, and so they're standard PLD models, and so you didn't write any software, you just make a chip. And it was very nice. It didn't matter where you put logic in here, all ran at the same speed. It was wonderful, right? So software was blazingly fast. It was simple. Delays were absolutely predictable. There's this problem that the logic, there's this quadratic thing here. So as process technology scaled, this scaled badly. You had this array that was a quadratic thing, wires that span the whole chip, bad, right? So what was about FPGAs? FPGAs broke that up and said, okay, I have these logic blocks, and now I have this problem that I have to do placement. Okay, now I got to do placement. This NP complete thing. My delays are no longer dependent on the chip itself. It's where I put things, so they're unpredictable. But the big thing here is this can take advantage of process scaling. So this is the big thing with FPGAs, it takes advantage of process scaling. And it's, nowadays we look back and say, oh well, that's kind of obvious. Back then it was not obvious at all. Anything that scales quadratically going up, scales quadratically going down. So when it's small, these things are pretty darn equivalent. In fact, when it's small enough, that's a good idea. So back when FPGAs were invented, when the first FPGAs were out, 64 logic blocks. Not 64 million, right? Not 64,000, right? It's a number you can count on your hands and toes if you're a mutant, right? So that's what it is. Not only that, 64, well, gee, 64 crossbar isn't that bad. Yeah, but it was the observation that this would then scale. So 128 3 LUTs, so about 64 logic cells as we count them today, or logic elements as other people count them today. The 58 I/O pins, 18 megahertz toggle rate. 18 megahertz, that was not the speed you would run your system at. That's as fast as you can build an oscillator on that chip and make it oscillate. And this cost a couple $100, and it was worth it. People bought them. And the reason, the proof that people bought them is, I'm still at a company with the same name. Otherwise, we would have gone out of business back in the 1980s. Okay, so this is the age of invention. What's important? Tight technology limits. That 64 logic cell thing, that was all the technology could deliver. Okay. So, efficiency is really important. Must innovate architecture. If you can come up with an architecture that can save 10%, that means you can make something 10% bigger than the guy up the street. It can run faster than the guy up the street. Very important to really beat on the architecture. Also very important to beat on the process. At that time, there was this thing called antifuses. Well, we still have things called antifuses. And instead of those SRAM cells which we were using, which are ridiculous, right? It's 6 transistors just for the darn switch, which nobody's paying you for, right? You can have 1 transistor, and then, when you program it, you blow it up. It's actually very efficient. Okay? So, innovate the process. In fact, back in this time frame, the largest capacity FPGAs, the fastest FPGAs, were built out of antifuses. Not true anymore. There's a good reason for that. We'll get to that. So, because there's no uniformity, vendors have to own the tools. Okay? So if you want to make modifications to your architecture, but you had to go to Data I/O to make a modification to your architecture, some other company, they would just maybe they would just say no. And if you had to build the same thing that everybody else was building, then you were in the commodity business and you couldn't really make any money, you couldn't innovate your architecture, you couldn't make improvements. Bad idea. Vendors have to own the tools. Today, vendors own the tools. How about that? Not generally recognized during this time frame, design automation is secondary to capacity. Hold a minute. Steve, you're crazy. It's all, efficiency is what it's all about. Efficiency of design, my time is what it's all about, right? No. If you could save, because the connection from here to there was set up because if you're making a state machine, take that wire to that switch, to that wire to that switch, that was the right thing. And if it took a human being to find those, that was still okay. You only had 100 blocks, it's no big deal, right? So, design automation, yeah, it would be nice if I could push the big green button and have the right thing happen, even if it took a couple of hours. But in fact, yeah, it's not that important. I can make people do that. What do applications look like? Okay, I got 64 flip-flops. I got, handfuls of flip-flops. FPGAs are smaller than the problem size. Okay. Oh, what are we actually using these things for? Well, maybe I could build cool arithmetic. Maybe I can, really what I really need to do? I need a multi-chip partitioner because my problem is really big and I have all these FPGAs. I have some automation to partition them into multiple chips. And so that was a big deal too. But FPGAs in this time, they were glue logic. They were the mortar between the bricks. And the bricks were your microprocessor and your memories and any other custom logic that somebody else built. It's actually not too uncommon to have an FPGA next to an ASIC to fix the busing problems that the ASIC guy forgot and didn't get the right interface between his blocks. So this led to what I call the architecture of the month. And so yeah, new architectures came up very rapidly, and some were much improved or appeared improved. There's actually a really interesting way. How do you make something efficient? Well, you make something efficient by not wasting. Every engineer knows that. Oh, so you make fine grain, really small logic blocks, so I don't have to waste any. I make wires that are very short, so I don't have to waste the dangling end of the wire. If the wire is five pitches and I only have to go 3 pitches, I wasted almost half the wire. Bad idea. A lot of architectures, cellular architectures, and then boom. What happened? So, that process technology is moving along and killed a lot of FPGA architectures. Xilinx got rid of an anti-fuse architecture, Xilinx got rid of a cellular architecture, we got rid of a high performance and multi-context. Big companies that were in the FPGA business got out of the FPGA business at that time. Process technology made a qualitative difference in what we're building. And that's what I'm talking about next. Because this is the end of the age of invention in FPGAs back in the early 90s. So here's what's going on to the mid-90s. LUT count, yeah, we know LUT count got bigger, but what got bigger faster was the wire length. Because we had CMP and we can have more metal layers. So actually wire length grew faster than LUT count. And that led to the age of expansion. In the age of expansion, well, actually before I jump into that, what's going on? And I take a big step back, and some of you old timers will recognize this slide, and there will be a few others that you old timers will recognize that we don't really show much anymore. This is the crossover point. It says, gee, why should I buy an FPGA when I can make my own custom chip? Okay, here's why. Because if I buy FPGAs, if I buy some number of them, I get that blue line. The slope of the line is the cost of one chip. So I buy 10 chips, it costs me 10 times as much. If I'm building my own custom device in my own ASIC, I'm on the red line, the slope is lower. Each chip is cheaper. But I have some NRE costs, and so there is a crossover point. If you're only going to, obviously, if you're only going to buy one chip, you're better off buying an FPGA. And so where is that crossover point? It's out somewhere. It's possible to compute that. It's pretty straightforward. And then an interesting thing happens, though, as the technology goes on, yeah, the slopes of the lines come down because devices get cheaper. But the NRE cost was going up. And so the new crossover point was farther out. So every generation, that crossover point moved down. So every generation, while the process was moving along, it was more reasonable to be buying an FPGA for some number of units. Okay. Well, so process generation was making it more reasonable. you know, pushing that crossover point out to higher and higher counts, thousands, tens of thousands, wherever it went. Okay, well that only makes sense if you can actually do it, right? If it actually fits in your FPGA. And remember we were talking about that problem. FPGAs are smaller than the problem size. Here's the second thing that happened. So here is a carefully measured distribution histogram of the design sizes from back in the 1990s. And so this, well, let's take this could be any parameter actually. Well, let's just call it design size. So this is the size, and there's some average ASIC design that people are kind of want, and there's some really small ones that people build. There's some really big ones that people build. Okay, well, FPGAs are someplace in 1993, and they can meet that requirement, that fraction of the size. Well, by making bigger chips, by following Moore's law, which you can do on an FPGA that you could not do in a Field-E, I can beat some more, and that volume is much bigger. So when I made the next bigger FPGA, this was a big deal. It admitted a lot more business. I mean, in marketing terms, it's called TAM, a total addressable market. So whatever. Oh yeah, I can, you know, maybe in a couple of years I can increase that by a factor of 10 for the number of ASICs. This is a big, big deal. This is a big lever and led to rapid growth. Now you're going to say, hold it a minute, Steve. The yellow curve moves, right? Because it's Moore's law and it's moving too. But it didn't move as fast as the FPGA line, and here's the proof. So back in the 90s, there was this thing called the design gap, which was promoted by EDA companies who wanted to sell more EDA tools and justify investment in that. And so they had, okay, see this line? That's the Moore's law line, but only the average ASIC start was much lower than that. So there's the proof that says, okay, yeah, designs just weren't growing as fast as Moore's law would let them. Okay. So, but FPGAs are on the Moore's law line. And so in about the year 2000, the biggest FPGAs crossed the average ASIC design start line, which caused no excitement whatsoever. Because everybody recognized that, oh, that's a $1,000 chip. That's the average ASIC size instead of a $40 chip. That's not interesting. But it wasn't long after that a $10 FPGA crossed that line, and that changed the whole equation. You don't see this curve anymore. You don't see this discussion anymore. You don't see talks about small ASICs anymore because they were gone. They're all FPGAs. The crossover point had moved out far enough, and FPGAs could do the job. Not just in size, but also in performance. Here's another graph that we had from ages ago. And this is showing how far can I get in a certain amount of time. So if I picked, for example, 2 nanoseconds, in the Xilinx 4000 XL, I can get to 5 LUTs. By the original Vertex, I get to about 20. If I can get anywhere on the chip in Vertex 2. And that's a combination of process technology, but also architecture. I have long wires that span the chip. I'm willing to waste wire. I'm willing to waste. Okay? Which I wasn't able to do in the Age of Invention. I didn't have the process technology that could deliver it. If I wasted, then I probably made something that was too big. I couldn't sell any of them. I maybe couldn't even manufacture any of them. Real big difference. Oh, another big difference is, with that expansion, every year I was getting twice as much stuff. That 64 eventually did turn into 64,000. You're not going to have somebody sitting down there clicking on buttons and routing them all manually. Automation was essential at this point. So this is when design automation took over, and this was important for design automation. I need to have a tool that can make make decisions that are sort of approximate, and they're still going to work out pretty well. So, what happened in the age of expansion? FPGAs went from technology laggards because nobody wanted to deal with a fabless semiconductor company at that time to technology leaders, where the foundries realized that FPGAs were good technology to prove their process on. We rapidly got to the front of the process technology curve and have remained there ever since. Rapid scaling, large devices, and the lesson was ride the technology curve. How much improvement can I get to deliver density by fiddling with my architecture? 10, 15%. How much can I get by sitting on my chair and waiting for the next process generation? 2x. Okay, so every 2 years, process engineers made us look like genius. Okay, now not to say none of that happened, but the big lever was not that I could do a more efficient LUT. or figured out a better pip pattern. The big lever was ride the process technology curve. What did that mean? Well, things like antifuses, which were a good idea, became a bad idea. Because when you're on the forefront of process technology, you get wires and you get transistors. And then sometime later, you get other things like antifuses and flash memory and all sorts of other goodies. Sometime later. It was a generation later, and sometimes 2 generations later. So from a technology perspective, if I want an antifuse device, I had to pay double for it, because it was on a process that was 2 years old. And this is when when SRAM beat antifuse and became the winning technology. And this is why. FPGA approaches the problem size. We saw that crossover point that even a $10 FPGA was as big as the average ASIC size. So what happens? So large, interesting applications fit inside one chip. Nobody's talking about multi-chip partitioning anymore. It fits. I don't have to worry about that. And then ease of design. Synthesis flow, this is when synthesis flow dominated. And all those interconnect-starved architectures, all those ones that were nearest neighbor connections, meshes, gone. Bad to automate, didn't give good results. They were the age of expansion architectures died. Age of invention architectures died in the age of expansion. So in the year 2000, this is an actual slide from Xilinx's actual marketing, except the little box above. This is the year 2000. This is the age of expansion. This is Xilinx saying what our FPGAs can look like over the next 5 years. And on this, the original vertex is this box down here. And we claimed 1 million gates on that, but there was some good math that went into that. But really that doesn't matter. What really matters is look at what's going on here. Look, in the next 5 years, I'm going to get to 50 million system gates. Now, ignoring for the moment what a system gate is versus a real gate, we don't even have this number, right? Today, right? We're barely at this number today. So this was 2005 is a prediction, and it didn't happen. What happened? This is a Xilinx marketing slide from 2005. It is not talking about 50 million system gates going to 200 million, right? It's talking about block RAMs and AES decryption, transceivers. It's talking about a PowerPC on it. It's talking. The word gate doesn't appear on the slide. This is a very different vision of what this device is. Okay? It's no longer in the age of expansion. This is in the age of accumulation. Let's see why. We go back to this slide. Remember when we last saw this slide, a small increase in capacity led to a great increase in addressable market. Once you get over the hump, an increase gives you diminishing returns. I compare this section with everything I had before. Now I'm working as hard as I can to make the next bigger device or the next faster device, and it's giving me incremental improvements, percentage points, rather than 2, 3, 4, 5x. I'm not getting a lot of return on this. Simple scaling isn't doing the job. Okay. So in the age of now we're in the age of accumulation. What's going on? So the first thing is it was the end of Denard scaling. So we had to trade off power and performance. And then the complexity of the technology, I said, it eliminates casual ASIC users. Up to that point, if I kind of think I want to build a custom piece of silicon, maybe I'll kind of do that. And I'll just do that. And if I make a mistake, well, I got to apologize to my boss and so on. After that, if I make a mistake, I got to apologize to my vice president, the CEO, the shareholders, because it's cents per share of making that mistake. Okay, so casual people kind of dropped out. Crossover point was high enough. Performance and capacity were good enough. It was all okay. Now, it's not to say they're gone. People are making custom silicon today. But the custom silicon's the niche, not the FPGA the niche. Got a lot of money out there, but still, they can charge a lot. Okay. What do the applications look like? Moore's law gives you more logic, but it doesn't give you more pins. FPGAs are now larger than the problem size. Well, there's nothing wrong with that, but nobody's going to pay you a big bonus for being too big for what they want to do. You pay a lot more money for a car that goes too fast, faster than you would ever want to drive. Well, maybe you do, but not a lot of people. So complete systems. So what a company, we're building libraries, we're building logic generators, trying to fill these chips up. Things to catch on here: power, performance, whole system standards. If we're doing a whole system, the standard matters. And how do I actually squeeze more of this, especially this power performance question? How do I squeeze more out of it when I try to trade them off against each other? How can I do that? I can do that by removing the programmability. I can build hardened logic blocks. This is the age of accumulation. It's no longer about just following Moore's law and making more or less. It's about other things that are being put in there. And that was what was on that slide. It's all that other stuff. Very proud of all that other stuff. The other thing that happened, it really kind of had nothing to do with Moore's law, was the winning application. And this is kind of missed on a lot of people in the FPGA business. The winning application was communications infrastructure, network routing. Okay? So this wasn't, before that there was all this talk, oh, we were doing these logic emulators and you're good for ASIC replacement. Okay, well, once you've done that, now what do? Okay. There's a winning application. FPGAs are really good for this. I built my custom data paths, hundreds of bits wide. I can really pump data through this. I'm building, there's this whole internet revolution thing that you might have heard about. That and there's companies like Cisco became the biggest buyer of FPGAs in the world. Okay, this is what's going on. So there was a winning application. Keep that in mind as we go on. Well, now that we have 2008, what is this the age of? And before I answer that, actually, I take that. Well, I'll spill it. I'm not going to quite answer that, because I come to a university, I expect them to answer that. So, but let's frame the question. All this time, I've been talking about process technology and I've been talking about applications. So let's talk about technology and applications. First, technology. Okay, what's going on? We know this. If you were, this is a source from CPUDB at Stanford. Frequency stagnation. Okay, end of Bernard scaling. Got it. Okay, no problem. Understand this. Been laboring under this ever since. Gee, you're gonna have to do something remarkable in this space. I/O bandwidth. Talked about this before. Yeah, Moore's law gives more logic, but it doesn't give more pins. What do you do about that? Well, the first thing you do about this is say, okay, I don't have to do this, right? Good engineer looks at that and says, this is really a problem? No, it's not really a problem because it's really about Rent's rule, right? I don't have to do it. I don't have to track it, but I got to do the 2/3 power. Okay, so now rats. That was a good argument, but it didn't quite work. So we're falling short on that. Package pins falling short. Internal package bumps falling short. What do? Actually, what we've done is we've increased the frequency a lot on I/O to get the bandwidth up. The next one is this one. This is IVS graph, and in fact, it's saying the cost per transistor is going to rise, and there's some argument about this, particularly from Intel, that says no, we're not going to let that happen. We're going to keep cutting the cost per transistor. In fact, it really doesn't matter, because really what's happened is. It's no longer dropping by a factor of 2, right? So we're getting 20%, 25%, and in fact, if it goes up a little bit, it's in the grand scheme of things, it all has the same result. The result is, as an engineer, I can't throw transistors at this problem anymore. I could do that in the age of accumulation. In the age of, what am I going to do? I will drop a microprocessor onto here. I'll drop 4 of them onto this device. And in the words of one Xilinx vice president at the time, I'll put 4 microprocessors on the chip. I don't care if our customers don't use any of them. They're free. Okay, well, they're not going to be quite free. I can't make decisions like that anymore. I can't throw more memory onto the die and say, if we have a little extra memory and it's wasted, it's free. It's not quite free. It never was free, but it's not as free as it once was. Okay, so there's the next one. Process technology kind of, dealing with those issues. So what are the kinds of things we're doing? The first thing was, 3D or 2.5D or whatever we want to call it. So how do we deal with this? How do we make really large devices? How do we deal with this bandwidth issue? And okay, if we put it inside the package, I can build really high capacity devices inside the package. So that was kind of the first one. Yeah, I build an interposer, it gives me a few extra layers of metal, and lowers my overall cost of making a really large die. Oh, and then the second answer is, oh, I don't have to stop there. I mean, putting the two identical die or 4 identical die is kind of no great excitement. But if I do something really clever, like I build an FPGA off a low power process, and I build a transceiver off a high performance process, and I put them together in the same package, and I take advantage of the very high bandwidth between them inside the package, then I get the best of both. I get a device that has power consumption numbers from the low power process, performance numbers from the high performance process where I need it. And so I get something better than what I could have done monolithically. Okay, so I kind of break a constraint that had been part of process scaling for 40 years. Part 2 is money. Okay, so we're engineers. I'm allowed to talk about money. The definition I once heard about engineers is an engineer is someone who can do with $1 what anyone can do with $2. So it has all the relevant aspects of engineering. The first is it's doing. So engineers do things. It involves money, and it's quantified. So that's all engineering in one statement. But let's talk about money. Through all this process, design effort has grown. And it's actually grown even non-linear, and even not smoothly. Particularly in that transition from expansion to accumulation. In expansion, it was just more of the same. Yeah, my place and route was slow, but it was just place and route. Now, if my place and route is slow, it's slow, but then I got to deal with these little memories in here and multipliers and whatnot. I've got microprocessors and I've got busing issues. I have qualitative changes because I have new dimensions in design. So design cost has gone up. This is the ASIC design cost. Actually, I said FPGAs caught the ASIC disease, right? So the same sort of problem. But we're all the same problem. Design costs are going up, and they're going up a lot. Okay? So just kind of put the scale on here. If let's take a number. If you think if it's going to be about $100 million, U.S. or Canadian, doesn't really matter too much, to make the next device. Okay. Well, that's expensive, but if I make enough money, it's not a problem. All right, it's all about money, and we're engineers. Okay, but how much money do you have to get? Well, if your company says I spend 10% of my revenue on R&D, and I just spent $100 million on R&D, that means I need to get a billion from sales of this chip. And so and depending on where you set your company's dividing line, you may need 2 billion. Okay? There just aren't a lot of chips that make that much money. There are some, but there aren't a lot of them. And so sort of kind of the economics of this whole thing has gone into a whole new scale. So companies can't do it. It's not just about it's expensive. It's just I can't justify this to my shareholders. Okay, but this isn't lost on anybody. So if I'm in the ASIC business, what do? I'm not going to make something that's going to only go in one socket. I'm going to be much more clever than that. I'm going to make an ASSP. I'm going to make an SoC. I'm going to make something that's programmable, and then I can sell to a lot of different places, and I sell $1 billion worth. So basically, what happened was, did FPGAs win against gate arrays? Sure did. Did FPGAs win against ASIC? No, because this is where they went. Okay, but that discussion isn't done. So. This other next observation is, okay, here's that observation. Look at that. Even starting back in 2000, microprocessors on here, whether they're hardened microprocessors or they're soft processors, they're there. And yeah, we're just, these devices all have them. What's with that? Well, let me take this look at this view of, this is Case Visser's view of computation. Well, if I have, just pick a data rate, but what we really want to look at is clocks per sample. And I can look at things like, if I have things like human interaction, then I've got 1,000 clocks per second. Okay, and I can have a microprocessor do that. Okay, but if I've got other things that are around Now I've got control and communications things. I'm not 10 to 1 or 1 to 1. I've got to have a fully pipelined system. Okay? Can't do that with a microprocessor. Got to build something out of logic. And if I've got to do something like 1 to 10, well, now I've got to actually replicate logic. I've got to have that flexibility in my system. And actually, I've got to have all this stuff to make a real system. And remember, the chips we have are as big as, they're bigger than the problem size. It's all fitting in. It's rattling around inside that device. Okay? So what do you kind of, you want something, you got to do RISC processor type processing, you got to do folded data paths, pipeline, replicate data paths. And so what do the FPGA companies say? Look, I know how to make something like that. I can make something that's got all this stuff in it. Okay? That's not just Age of Accumulation. It's now targeted to that specific problem. And it's actually very different than the data pumping pipeline machine that we're building for communications infrastructure. They don't need the processing system if you're building a wide, fully pipeline. They only have one of those problems. Okay, here we have processor subsystems, programmable logic subsystem, programmable analog to digital conversion. Why? Because these things are really interfacing to the real world. Programmable busing, I got to move stuff around. So that's sort of what are these guys doing? Well, we're still going after the last of the general purpose logic business, while we're definitely pumping out devices that are for the communications infrastructure where our bread and butter is made. I have a quick slide here on, got to do that, and you got to program that. I hinted at this before, and I'm going to gloss over this one here. But basically, it's okay. How do you program this? You program it you got to raise the level of programming, and you do that two ways. You raise the level of abstraction to C or OpenCL or something, and you include pre-tested design blocks. So that's how we get to standard interfacing in the IP libraries. It's the only way this stuff can get. You can put enough into these big devices to use enough of it that you buy the expensive ones and pay us more money. So I want to, as I conclude, I want to highlight this is a cool little gadget you look up online, the Phenox, because it kind of rolls all this stuff together. It's a fun thing. It's a quadcopter, obviously. 2 cameras, microphones, and all that jazz. The cool thing is it's autonomous. It can fly around and avoids obstacles. The other cool thing is it obeys gestures and audio commands. So what's going on inside here? Okay, it's flying and controlling all this and avoiding obstacles. It's got to do the image processing to do that, right? All of that. Okay, so there's image processing stuff going at a very high data rate. You need the programmable logic to do that, or you don't get it done in time, and you run into the post, right? And then it's making decisions at robotic type speeds. There's a microprocessor in there making those decisions. So it's basically, and it's programmed in OpenCL, which I thought was pretty cool too. And of course, for me, the best part about this is, the only way you could do this is if the hardware is light enough. Right? Like there's not a rack of computers somewhere else and I'm communicating back with it. It's all sitting in that one Zinc processor on there. So, gets us to this question, what is the next age? And when I look at this, I really see us getting back away from where the process technology, where the process engineers were making us look like geniuses every couple of years. That we're no longer getting, technology is no longer improving at a rate that, frankly, that we expect. And so it pushes the burden back onto the designers and EDA, to be able to build things that run on these platforms and build them quickly enough to get them out and get used in a reasonable time. So I think this is the age of the design engineer. I think we've been in it for almost a decade. We've never totally been out of it. And just like through all the ages, there's been invention and architectures all through the ages. There's been expansion in process technology. There's been accumulation of logic blocks. And there's been EDA and the design engineers have put in a great deal of effort through all that. The question now is where is the greatest effort going to be? Who holds the baton to make the next big stride forward. And I think it's design engineers. We hold the baton. That's what I got to talk about. So go build great stuff. That's all. We'll make platforms that hopefully will make you look like a genius. So that's the end of talk one, and we can chat about that, or I could just launch right into the next
Well,
one.
let's just thank you for that talk.